gonna hit the lights. So the stop box is in the corner. I don't know if you can see that. There is a stop box. So what we are talking about today is the application of geometric sequences. So on Friday we talked about the general term for geometric sequence. We have a formula that's in our formula packet that we can use. When we know a sequence is geometric, we can plug in the common ratio in the first term and the term number and figure all that stuff out with geometric sequences. So today, with the applications of geometric sequences, what we will have is we're actually going to get a slightly modified version of that formula to use for application problems. And then we will look at things like population growth or financial investment for these types of problems. So, oh, there you go. Don't forget your stop box. It was kind of invisible. I almost thought it wasn't there. And here is the compound interest formula. Now, this one's not in your packet, so make sure you write it down. You can't just look to your packet, but it's very similar. It's slightly modified. So it's use of n plus 1 equals use of 1 times r to the nth power. So the only difference from Friday is basically this is not n plus 1, it's just n. Use of 1 is still our first term, but when we think about it in terms of these application type problems, use of 1 is usually like the starting populations. It's still the first term, it's what we start with, but it's the starting population or like the initial investment if we are talking about money. For these application problems, the R begins to stand for the rate. And we've had some problems dealing with rate before when we have talked about exponential growth and decay. So you will note that stuff seems familiar, or should seem familiar. N is the number of compounding periods. So we will look at some examples that are mostly in years, but if we're looking at like population growth over a certain amount of years, N would be the number of years. And so then when we use this formula, we'll be able to figure out how much we have after a certain amount of time. Do you guys remember when we did the compound interest stuff, when we worked with exponential growth? There was something special we had to do to the rate. We couldn't just like plug in the percent. Does anyone remember that? I'm about to remind you if you don't, so that's okay. But keep in mind that we write that rate as a decimal, and then we add 1 to it. Remember that adds the amount of interest or the new growth to the initial amount, whatever that happens to be. So that's why we have to add that 1. So just a little example to jumpstart your memory with this. If the growth rate is 25%, we would convert that to a decimal, so it's 0.25, and then add 1 to it, so the rate we would use would be 1.25. So that 1 adds that initial amount in with the interest or the new growth. So we're going to start with a population example. We're actually going to do a two-parter. So we're going to use this example or this question for 2 examples. So we've got an endangered species of marsupials, and they have a population of 178. There's only 178 of these ambiguous marsupials left. However, with a successful breeding program, it's expected to increase by 32% each year. So the first question we're going to find out is find the population size after 10 years. So there's very few of these marsupials left, but if we implement this breeding program, the population will grow 32% each year. So that's the modified formula that we are going to use for our growth. The u sub 1 times r to the nth power. So now we have to figure out what numbers go where. So u sub 1 is like our initial amount. So how many marsupials do we start with? So 178, that will be u sub 1. Now the rate is 32%, so keep in mind we have to change that to a decimal and then add 1 to it. So 1.32 will be what we use for the rate. And then what's the compounding period? How many years are we looking at here? 10 years. So 10 will go in for n. So we're looking at what's our population after 10 years. So then we can put all of these things into our formula. So 178 times, I'm not going to actually use the x, I'm going to use parentheses. So 1.32 to the 10th power. Now, if you want to put that all into your calculator, that should really be all right. I don't foresee there being any issues with this formula. Now I'm going to just write down all the digits I got to start with. So we got 2,858.639 marsupials. So if I want to use 3 significant figures here, how would I round this? Absolutely. So I will look at that 8, that's going to round that up. So for 3 significant figures, you've got 2,860 marsupials after 10 years. Wouldn't that be awesome? That endangered species going out? I know that formula is a little bit different from the one from Friday, so are there any questions or any issues with using it or the rate or anything? Right? Like I don't know enough about like the classification. Like will they still be endangered when it reaches this amount or would they just be like threatened or
probably that's still not a lot.
Right?
You look in like a book or something.
No, I feel like when I was little I used to like reading about all the kinds of animals and stuff. Alright, same examples, you don't need to rewrite that, but I want you guys, without my help, to calculate, okay, if we keep this breeding program going, how big will that population be after 25 years? I'm just rewriting the formula, but you guys go ahead and figure that one out. Alright, what'd you guys come up with? How many marsupials will there be up to 25 years? Okay, so Jerome, what did you get? So if you did not get 184,000 marsupials, you should probably have me check your work, kind of figure out what's going on and where that breakdown is happening. But that's how much we should have. And again, I don't know, do you think they would still be endangered at that point? No, probably all good. All right, our next example is dealing with finances. So you invest $2,500 at a 1% interest rate per year. How much will it amount to after 5 years? And then, how much is interest? So then, what's our initial investment that would go in for use of 1? Very good. 2,500, so that's use of 1. Okay, what do we put in for rate? This can be tricky. It's really easy to make a small mistake on this one. Aha, 1.01, because if I change that to a decimal, it's actually 0.01. So when I add 1, it's 1.01 for my rate. A lot of people, I think, want to just do 1.1, so be careful with your decimal places. And then what's the compounding periods? How long are we keeping this money in there? 5 years for N. So definitely need to be able to pick all those things out. If you are having issues, you need to speak up and let me know. Because then we can plug all that in there. So 2,500 times 1.01 to the 5th power. So I leave that in there. How much money are we gonna have? And we can just leave this one. Let's take this one out to the cents, because we're talking about money. So out to how many cents? Do you guys just not like calculating? You just like me writing the numbers out? You gotta know how to do it on your own though too. I calculated $2,627.53. So after leaving our money in there and not touching it for 5 years, that's how much we would end up with. So how do we figure out how much is interest compared to how much we originally started with? Any ideas? What are you thinking? Yeah, absolutely. See, you guys know what's going on. You just don't want to tell me. If I subtract my initial amount, okay, let's figure out how much is interest. Subtract from the initial amount. Leaving that money in there for 5 years only made $127. Can you believe it? Why is it such a small amount? Yeah, it's only 1%. So really think about that. Like, as you guys, I know you're not all grown yet. You got a year or so left, depending on where you're at. But when you guys are looking at investing in your future, when you become adults and you start adulting, look at that, like, interest rate. Because usually, like, things on, like, savings accounts, usually the rates are actually lower than that. So you're not really going to earn a lot of money by putting stuff in that. So it's just kind of something to keep in mind as we move forward. Any other questions on this? All right, so we're going to hit the stat box, and then we're going to have one final sort of different type example, and then we will be done with the notes. So my question for you is, moving forward here, how will you know when you should use the compound interest formula from today versus the general term for geometric sequences formula that we talked about on Friday? Like, how will you decide when to use which one? How will you know when to use which problem? What do you guys think? Was there anything different besides the fact that they were like written in words? Anything different about today's problems compared to like the list of numbers that we were working on Friday?
All about interest.
They do have interest. I feel like you're onto something. So to have interest, to accrue interest, you need an interest rate, right? How are interest rates written to begin with? Percents. So I would say like that would be a clue for yourself. If you are reading a word problem and it has a percent in it, you want to use the formula from today. If you are reading a word problem and it does not have a percent in it, then you're going to want to use the original formula that we worked with on Friday. So that's something I just want to let you guys know, because even though all the ones we're doing right now are using that interest in the percents, you might run across a different type. So just keep that in mind. The percent, you should think, I should use the one with the rate in it. And then one last thing, just to note, and I know we saw this when we did exponential growth in chapter 4, but if you see the words per annum, that means each year. And again, I know you saw them on some word problems previously. But sometimes with this interest stuff, it's not always happening at the end of every year. Sometimes they accrue your interest at different points. Like it could be monthly, or it could be twice a year, or quarterly, which would be 4 times a year. So for example, if you were accruing interest twice annually, so 2 times throughout that year, in order to figure out your interest or the amount of money you're going to have, we actually have to divide our rate by 2 and multiply our years by 2, because we're getting that interest is being calculated twice a year. So that's why we have to multiply that by 2 for the years, so the end part of it. I know these are kind of weird, so we're going to go over an example of this all together. Just want to make sure you guys have a chance to jot that down. I think we're all good. So this example is about Mr. Jones. He's got a little bit more to invest. He's investing $5,000 and his account is earning 12% interest. It's actually compounded twice annually. So how much interest is earned after 10 years? So we see that there's a percent in our problem, so that should be our clue that we are going to use u sub 1 times r to the n, not the n plus 1. And then we can figure out, what pieces go where, and it might take us a little bit more than usual. Our initial amount should still be pretty obvious. You guys okay with that? The first amount of money you start with is $5,000. Now, for the rate, because it's compounded twice annually, we'll start with taking that 12% and writing it as a decimal, so 0.12. But because this interest rate's for the whole year, but we are compounding it in the middle of the year, we actually have to divide that by 2. So then I've got 0.06. And then we have to add the 1 to it so that we include our initial amount. So 1.06 is what we will end up using for the rate. Now, how many years are we leaving this money in this account? Well, it's compounded twice annually, but how many years? 10 years. Okay? So that's 10 years, but it's happening twice a year. It will add up all this interest. So I'll actually have to do 10 times 2 and put 20 in for the number of compounding periods. And it matters because at half the year, they'll add up all your money and calculate your interest. And then they add that interest to it, so it actually ends up earning you more money because there's more that they are basing that interest off of by doing it so often. Once we have all that stuff, we can go ahead and plug it into that formula. So I've got 5,000 times 1.06 to the 20th power. And so we'll also see that because we've got a higher interest rate and because we're being compounded annually, Mr. Jones is earning a whole lot more money than we did. He's also leaving it in there longer than we did too. So I ended up with $16,035.68. But that doesn't quite answer the question. What's our question? How much interest? So we'll have to go ahead and subtract the initial amount to see that the interest was actually $11,035.68 for our interest. So that's how much money was actually earned, just letting it sit in there and that interest compounding twice a year, that 12% interest rate. So I know those ones are a little bit tricky, so if you need help when you are going over those on your assignment, make sure that you speak up when you get to that. Any questions right now? You guys, this is the cutest picture in the whole book, and it's on this section. It's like reindeers in love. Alright, so D2 is all about like the population growth type stuff, and D3 is like the money and finance type stuff. So these guys go hand in hand here.